and I'm going to ask if you have any questions.
Not really. I haven't even got through that much of the lecture so far. I just kind of wanted to like hopefully see you work through some homework problems, maybe get a better understanding of it.
Fair enough. I will ask you to look at the lectures from 2 days ago on Wednesday. Yesterday's lecture is basically how to do the lab that's due
Okay.
next Wednesday.
Do you mean the
You don't-
Q&As?
Yeah, I put the actual lecture for the lab in Q&A, and I put it as an extra lecture right underneath the lab that says titration of juice to determine vitamin C content.
Oh, okay.
So that's the lab that I talked about yesterday, and I recorded that, and I put a little extra lecture
Oh, I see. Okay.
in the module. And so when you open up the Q&A and you look at the lecture for yesterday morning, it's the same lecture.
Okay.
So I will be posting last night's lecture. I haven't done that yet. It's another lecture about the lab. But basically, I go through the lab step by step on how you need to do it.
Okay.
And so it should be very easy and very pleasant and kind of fun.
Yeah.
You see color changes and things like that.
Is that for the compound or the vitamin C one?
That's for the determination of that's for the titration to determine vitamin C content.
Okay, I see it. Okay.
And with all of these labs, you definitely don't want to wait till the last day to do them, because there are certain things that you need to buy sometimes that if you don't have them at hand, you can't get them later. Like for the vitamin C one, you need to have a box of juice or a pouch of juice where you know the vitamin C content.
Okay.
And so that would normally be on the label. And if it's too late, you're going to have to go to Winco and buy some.
Yeah, that's not fun.
Yeah. And you don't want to do that at the last moment. Okay, so I'm going to do a change share. And I'm going to share my desktop here. And a lot of these problems I've already done in previous lectures, so I'm going to skip them.
Okay.
And go to other problems where we do the same thing, but with a different problem. So that'll give people a chance, and you a chance, to see more problems if you look at the older Q&A. So I'm going to go through these very quickly and push the ones off to the side that I've already done in another Q&A.
Okay.
And again, it's because what I've done in these, we're going to be doing in other problems, the exact same thing. So I will point out to you that here we're given a mass of 0.750 grams of this aluminum hydroxide.
Mm-hmm.
And we're asked what mass of water would be produced and what mass of hydrochloric acid is required to react with our 0.750 grams. And this whole process is called stoichiometry. So this same one, you can see they're asking for the mass of iron from 454 grams of iron 3 chloride. Excuse me, iron 3 oxide. So basically, it's one of those things where you're given the mass of something and you're asked to get the mass of something else. So we've done all these problems. This one, it's about mole to mole, but that's actually an easier problem. You'll see when you look at the older ones. The combustion one we've already done. There are more combustion ones later. Mm-hmm. This one is a limiting reactant one. This one has been done, but there are limiting reactant ones later. This is a limiting reactant one, and limiting reactant ones are also later. So this is one that I haven't done for any other Q&A, so this is where I'm going to start. And you may have heard me say, oh, this is a limiting reactant one. We'll be doing a limiting reactant one later. And you'll notice it says limiting reactant.
Yeah.
Okay, so the idea of limiting reactant is if you start with 1 gram of aluminum and 1 gram of chlorine, will you run out of one before the other? And therefore, that one that you run out of first, that will limit your reaction. So is one of these limiting, and is the other one in excess because you'll have leftovers? So limiting means that it's all used up, and excess means there's leftovers. So there's my definition of the limiting reactant. It's used completely. And we also use this to determine the amounts of products. The example I give in previous lectures is if you have one bicycle frame and two wheels, you'll be able to make one bicycle. If you have 5 frames and 20 wheels, you're going to run out of frames first, so you'll end up making 5 bikes and that's it.
Mm-hmm.
So the 5 frames would be used up completely, and you use the 5 frames to say you get 5 bikes. On the other hand, if you had 5 frames and 5 wheels, well, let's make it 4 wheels. With the 4 wheels, you could only make 2 bikes, then you'd run out of wheels. So if you had 5 frames and 4 wheels, the 4 wheels would be the limiting reactant. Does that kind of make sense?
Yeah, that makes complete sense.
Okay, so the excess reactant, it's we have leftovers. And why do we have leftovers? Because the limiting reactant ran out. Okay, so this says if you begin with 2.70 grams of aluminum and 4.05 grams of aluminum or of chlorine, what is the limiting reactant? So I'm going to show you 2 ways of finding the limiting reactant. I like one way better than the other. So here we have 2Al plus 3Cl2. And usually when I'm doing these, I rewrite the reaction and I leave the state off because that really doesn't matter. So I've got 2.70 grams of aluminum and I have 4.05 grams of chlorine. And notice they want to know what is the limiting reactant and what mass of aluminum chloride can be produced. So the general way to do this is you take grams of A, turn that into moles of A, turn that into moles of B, and turn that into grams of B. Now, the way to turn grams of A into moles of A is to use the molar mass of A. The way to go from moles of A to moles of B is using the coefficients of your balanced reaction. And of course, the way to go from moles of B to grams of B is to use the molar mass of B. Okay, so the first way to find out what is limiting is I'm going to take 2.70 grams of aluminum and I'm going to find out how many grams of aluminum chloride I could make. So if I follow this pathway, I'm going to multiply by 1 mole of aluminum per 26.98 grams of aluminum, because that is the molar mass of aluminum. And right now I'm grabbing my book so I can look at the, I'm grabbing my book so I can look at the molar masses of the elements, because that's going to be needed. And 26.98, good. I got that one correct. And then, so this is my first conversion. I'm going to put a little A here, and this is A. And I'm going to call this B, and this next one here is B. I want to go from moles of A to moles of B, and I get that from up here. Since I want the mass of aluminum chloride, I'm going to first get the moles of aluminum chloride. So there are 2 moles of aluminum chloride to 2 moles of aluminum. Now, some people ask, well, if it's 2 to 2, why don't you just write 1 to 1? And the answer is I don't want to make a mistake. And if I just bring the coefficient down from the balanced reaction and not do the math in my head at first, I'll probably be better off.
Mhm.
Now, the molar mass of aluminum chloride, I have to do a little bit of computing here. Chlorine is 35.45, then times 3. Then I have to add the 26.98. And so I should get like 130-ish. And indeed, I get 133.33 grams of aluminum chloride per 1 mole of aluminum chloride. So you see here for C, I've used the molar mass with grams on top, moles on the bottom. For A, I've used the molar mass with grams on the bottom, moles on top.
Yeah.
What possesses me to use these differently? And the answer is so that units cancel. And once you're done with all of this, you will end up with your answer, and we can estimate the answer. 26 will go into 133 about 5 times. 2 divided by 2 is 1. 5 times 2.7 should be less than 15, but more than 10, right?
Mhm.
So let's see what we get. So we get 13.34 or 13.3 grams of aluminum chloride. And we have 3 significant figures because of this, 2.70. The balanced reaction, those numbers are exact, so therefore they have an infinite number of significant figures.
Okay.
So this is the maximum amount of aluminum chloride we can get from 2.70 grams of aluminum. Now, what if we started with 4.05 grams of chlorine? What's the maximum we could get? Well, here, instead of using the molar mass of aluminum, I'm going to use the molar mass of chlorine, which is 1 mole of Cl2 per 70.90 grams of Cl2. And then I'm going to use 2 mole of aluminum chloride to 3 mole of chlorine. Do you see how that's not a 2 to 2?
Yeah.
2 to 3. And then I'm going to still use my 133.33 grams of aluminum chloride to 1 mole of aluminum chloride. So when I do the estimate here, I think, well, 70 will go into 133 almost 2 times. 2/3 of almost 2 would be like, I don't know, 1.2, 1.3. And 1.3 times 4 would end up being like close to 6 maybe.
Mhm.
But in that range, 6-ish, maybe a little less. So let's see what we get. 4.05 times 2 times 133.33 divided by 70.90 divided by 3, and we get 5.07. 5.08 actually. Okay. So from our 4.05 grams of chlorine, we can only make 5.08 grams of aluminum chloride. From our 2.70 grams of aluminum, we can make 13.3 grams of aluminum chloride.
Mhm.
Okay. And when we think about this, we think, okay, so how much could we really make? And the answer is if there's only enough to make 5 grams, you can't possibly make 13 because you run out of chlorine.
Yeah.
Okay, so here, because this is the less amount, that means that Cl2 is limiting. And if Cl2 is limiting, aluminum is in excess. So if we take a look at the question again, the question is A, what is the limiting reactant? B, what mass of aluminum chloride can be produced? You can see right here, we have the answer to A and to B.
Mhm.
So what is the limiting reactant? Cl2. How much can be made? 5.08 grams of aluminum chloride. Now, if we take a look at C, what mass of excess reactant remains when the reaction is completed? Well, let's see if there's a way we can figure this out. Maybe a clever way. For C, we know that we have 2.70 grams. We know we have 4.05 grams, and we know we're going to make 5.08 grams, right?
Yeah.
So clearly these numbers don't add up because not all of your aluminum was used, correct?
Yeah.
So I'm going to cross this off because I know that all of the chlorine was used. How much aluminum was used?
2.08.
How do we figure it out? And the answer is, shouldn't this mass and this mass added together equal the mass of product?
Oh, right. Okay.
So you can see it's 1.03 grams of aluminum are used because that will add up to 5.08.
Okay. Okay. I see.
So I've got 1.03 grams of aluminum used, and I have 2.7 grams available.
Mhm.
So how much is left over? It's the difference between these two values, right?
So about 1.67.
Yep.
Okay.
So that's one way to do it. Another way to do it, though, is this says set up an amounts table for this problem. I'm not going to bother doing that. But another way to do this is the other way of finding out which one is limiting and which one is in excess. So this is another way to do it. Now we have 2.70 grams of aluminum and we have 4.05 grams of chlorine. And one is in excess and the other is limiting. And we don't know which one. Well, we already know, but let's see if this way gives us the same answer, okay? So I'm going to start with one of these. It doesn't matter which one. And I'm going to start with 2.70 grams of aluminum. I'm going to multiply by 1 mole of aluminum per 26.98 grams of aluminum. And so this starts off the same way as the other problem, right? Only this time, instead of finding out how much aluminum chloride I'm going to make, I'm going to find out how much chlorine I need to react with this. So I'm going to multiply by 3 moles of chlorine over 2 moles of aluminum, and then 70.90 grams of chlorine over 1 mole of chlorine. So I'm going to give you a chance to catch up on that while I do the math. Just a little FYI, when you're using your calculator, it works a lot better when you turn it on. Okay, so I get 3.55 grams of chlorine are needed. Okay. So how do I use this number? Well, I need 3.55 grams of chlorine to react 2.70 grams of aluminum. That's what this means.
Okay, I see.
Now we have we have a 4.05 grams of chlorine. Actually, let me think. for a minute here. This isn't coming out the same way as the other problem.
Yeah.
And I'm trying to figure out why now. So let's see. It's probably my using the calculator. 26 will go into that almost 3 times. 3 times 3 is 9, times that is 30, divided by 2 is 15. I don't think I got that number correct. So 2.7 times 3 times 70.90 divided by 26.98 and divided by 2. Yep, this number is not correct. See, this is what happens when you don't estimate.
Yeah.
So I get 10.6 grams of chlorine. So I'm going to take all this here and I'm going to cross it all off because it's wrong, because that was wrong. So we need 10.6 grams of chlorine to react 2.70 grams of aluminum. We have 4.05 of chlorine, so not all of the aluminum will react. Does this statement follow from the first one?
Yeah.
Okay, so if not all of the aluminum will react, what does that mean about it? The aluminum is in excess, right?
Mm-hmm.
But the chlorine is limiting. So we found out the same thing that we did before, except for a big thing. We don't know how much aluminum chloride we're going to make. So if we are going to find out how much aluminum chloride we're going to make, we want to start with the amount that we're going to be limiting the reaction with. So we'd start with 4.05 grams of chlorine, multiplied by 1 mole of chlorine per 70.90 grams of chlorine, and then 2 moles of aluminum chloride per 3 moles of chlorine, and then the 133.33 grams of aluminum chloride per 1 mole of aluminum chloride. Now I'm going to pause here, and I'm going to say here, you'll notice that the balanced equation above has 2 moles of aluminum chloride in the equation, but here I'm only using 1 mole. So why am I only using 1 mole here? Well, the answer is simple. If I use 2 mole of aluminum chloride on the bottom, I'd have to do 2 times 133.33 grams up top.
Okay.
And do you see how the 2's would cancel?
Yeah. Okay.
So I'm just going to use 133 over 1. I'm going to use the molar mass. And I am wondering, well, how do the coefficients come into play? Right here in that middle conversion, that's where they come into play. Fair enough?
Yeah, I got it.
Okay. So when we do the math here, we find that we get 5.08 grams of aluminum chloride, and that's going to be our yield. So that's going to be A here. This is A, and this is B. Now, what about C? How do we do how much is left over? Well, in this case, I think it's going to be a similar problem to what we did before. We know that we're going to get 5.08 grams of product minus our 4.05 grams of chlorine, means that we have 1.03 grams of aluminum used. And so we can figure out how much aluminum is left over by saying 2.70 grams of aluminum minus 1.03 grams of aluminum equals 1.67 grams of aluminum left over. Okay, so if you look at the two solutions, and when I say look at the two solutions, I don't mean we're going to do a comparison of the two point by point. The comparison we're going to look is look at all this work we did by finding out how much of one thing you need to react with the other, and look at how much work we did the other way.
Yeah.
No real difference.
Yeah.
So which way are you going to do this? And the answer is whichever way makes the most sense for you.
Okay, I was about to ask you that.
Okay, so I'm just trying to show you two ways to tackle the problem. And they do have this thing called an amounts table. I don't use amounts tables, so I don't teach them.
Okay.
But, you know, that doesn't mean you don't have to look at them, or should not. I should say that doesn't mean you should look at them. The reason they use amounts tables is so you can see how many grams react with how many grams and so forth and so on. All right. So if we take a look at this one, this is a limiting reactant problem. Now, there's no word in here that says limiting. What there is, though, it says is if you mix 100 grams of each of these, what is the maximum mass of aspirin that can be obtained? Well, that maximum mass will depend on which reactant is limiting.
Mm-hmm.
So I'm just trying to point out to you that there are other ways of asking you a limiting reactant problem without saying, hey, this is a limiting reactant problem. So this one is a little bit more difficult just because the molar masses are more difficult to work with. So I'm going to go for the molar mass here of the C6H4OH CO2H. And it looks to me like there's 7 carbons. Looks to me like we have 4, 5, 6 hydrogens. And we have 3 oxygens. So when I do this in my head, I get 48 plus 6, which is 54, and 54 plus 84, which puts it at about 138. So let's see what we get. $138.13. Now, the molar mass of this acetic anhydride, I think that's what that is. Yep. Is CH3CO2O. So here we have 1, 2, but because of the 2 on the outside, we have 4 carbons. 3 hydrogens in here, but since the 2 on the outside, we have 6 hydrogens. 1 oxygen here, but the 2 on the outside means really 2 oxygens plus 1 on the outside for 3 oxygens. So that's roughly 48 plus 6, which is 54, and 54 plus 48 puts it at like 102, right?
Mm-hmm.
Okay, so I got 468. I think I messed up. Oh. $102.1. And that's not right either. Let me try that again. Oh, 12.1. And it should be 12.10. All right, so those are the 2 molar masses. And then we need the molar mass of aspirin, which is right here. So what is the molar mass of that stuff? I'm just going to put aspirin here. And we can see that we have 6 carbons here, 7, 8, 9. 9 carbons. 4 hydrogens here and 3 here for 7 and 1 more here for 8. And then we have 1 oxygen, 2 oxygens, 3, 4 oxygens. So 4 oxygens is 64 plus 8.08 plus 9 times 12 is 108.09. So I get 180.17. Okay, so now we're ready to go because we have the molar masses that we need. If we have 100 grams of each reactant, how much aspirin are we going to make? So the wrong answer is 200 grams.
Yeah.
Which way would you like to do this?
I think the first way we did it was a little bit easier for me to grasp.
Okay, so then we're going to start with 100 grams. And here, this first thing here is called salicylic acid. So I'm going to put SA here for salicylic acid. The second one is called acetic anhydride, so I'm going to call that AA. And this one is aspirin, so I'm going to call that ASP, so that I don't have to write out the formula here.
Yeah.
So we're going to start out with 100 grams of salicylic acid times 1 mole of salicylic acid per 138.13 grams of salicylic acid. Now, if we look at the reaction, what are the coefficients?
Isn't just 1 for all?
There are 1s for all of them. So that means 1 mole of aspirin to 1 mole of salicylic acid. And then it's 180.17 grams of aspirin to 1 mole of aspirin. And we can see that we're going to get a bigger number than we started with.
Mm-hmm.
And the reason for that is because if you look at the aspirin molecule right here, compared to what we start with, we get a 1-to-1, but the one we get is far bigger than the one we started with. And that's why we get more product than reactant. Okay, times 180.17 and divided by 138.13. I used the wrong number. I get 130 point grams. I have to put the decimal there so I have 3 significant figures.
Okay.
If I don't put the decimal there, I've only got 2 sig figs. So now let's start with 100 grams of acetic anhydride. What are we going to put next here?
You're going to put 1 mole of acetic anhydride over the molar mass, which is 102.1.
That's right. And what are we going to put next?
It's going to be a mole of aspirin over a mole of acetic anhydride.
That's right. And you can see you're probably pretty thankful that we're abbreviating these things now.
Yeah.
And then 180.17 grams of aspirin per 1 mole of aspirin. And this one, I can look at the numbers and I can see that this is going to be a larger number because the only difference between the two calculations are 180 over 138 versus 180 over 102.
Mhm.
So this will be a bigger number, and it's going to be like 180. And it's 176. Okay, so again, how do we compare these two numbers? What does each number tell us?
It means that you'll need 130 grams of the salicylic acid. What was it called again? The SA acid.
Yeah, just call it SA. That's fine.
Okay, and then yeah, 176 of the AA.
No, what
Oh,
what do
wait.
these what do
Okay,
these
so wait,
numbers
never mind.
mean?
So you'll get 176 grams of aspirin if you react all of your AA, right?
Right.
Okay.
And the 130 means you'll get 130 grams if you react all of your salicylic acid.
Yes.
So is there enough salicylic acid to make this 176 grams?
No.
So that means we run out of it, right?
Yes.
So what does that mean about salicylic acid?
It's the limiting reactant.
So SA is limiting. And what does it tell us about AA?
It'll be in excess.
Excess. So which one do we use to determine the amount of aspirin we're going to make?
It's going to be the SA.
Right. So here, that means that for what maximum mass of aspirin can be made, it'd be 130 grams. This is the maximum. So the maximum is the smaller of the two amounts, which kind of runs contrary to looking at those two numbers. You think, well, one's 130, one's 176. 176 is more. That's a maximum.
Mm-hmm.
But the maximum is not based on what you could make from either of the things. It's what you could make maximum based on combining both of them. So this is the old, how many sandwiches can you make if you have an endless loaf of bread, endless loaves of bologna, and one tube of mustard?
Yeah.
And the answer is, well, it's going to be limited by your mustard. Not the greatest analogy because, you can eat a bologna sandwich without mustard.
If you don't like mustard.
Yeah, if you don't like mustard, it's like, what kind of question is that, Tony? It's pretty stupid. Okay, but personally, I need mustard on my bologna sandwich. It's the mayo I can go without.
I'm the opposite.
I saw this lady leaving the store yesterday, and she had her home bag, but the bottom of the bag was like mesh, and I swear she had like 3 quarts of mayonnaise in there. I was like, oh my God, I bet she makes potato salad like nobody's business.
Something.
Okay. Now this is a new one that I haven't covered for any section yet.
Okay.
Notice it says, what's the theoretical yield? And here, the theoretical yield is going to be the maximum yield. Okay, so this is a limiting reactant problem. But then it says, if you actually get 16.3 grams, what is the percent yield? So this idea is simple. When you do something like this and you're trying to collect, actually, we don't need to worry about doing the problem because it tells us how much you get.
Okay.
Okay, that's the theoretical yield. So I don't know which one of these is limiting, and I don't care. I'll be honest with you. The theoretical yield is 68.0 grams. Okay, now look at the product. It's a gas. How do you collect that gas? In a jar, right?
Yeah.
But how do you make sure none of it escapes? Well, you do the whole thing in one jar. Okay.
Yeah.
So you mix these in one jar, you get ammonia gas, and then you get H2O gas. So how do you get all of this gas and none of the H2O gas? And the answer is you do this in a jar and then you let it cool down and the H2O condenses.
Okay.
And then you open up the jar with a hose and you let all the gas come out into another jar, right?
Mm-hmm.
But how do you make sure you get all the ammonia out of that jar and into the other jar? And the answer is you can't. So you lose some.
Okay.
In addition, some of the ammonia gas will be dissolved in the H2O droplets. So you lose some there. So this is all in an attempt to purify the ammonia that you're making. So whenever you do a purification, you're going to lose some product. So how do we calculate percent yield? We're going to put some definitions here. I almost wrote on my paper. I don't want to do that. So some definitions. Theoretical yield. This is the maximum yield based on the limiting reactant. And so we've already discussed how to figure out the limiting reactant, okay?
Mm-hmm.
The actual yield. This is the amount that we collected and available for use. And this would be after the reaction and after purification. So what is the actual yield going to be compared to the theoretical yield? The same, more or less?
Probably a lot less, or a little less at least.
Should be less. The only time the actual yield is greater is if you haven't purified it and you have other junk in there.
Okay.
And it could weigh more than the theoretical. Now, the percent yield is actually a formula. And the formula for percent yield is as follows. So percent Y means percent yield is equal to the actual yield minus the theoretical yield over the theoretical yield. Oh, my bad. It's the actual yield over the theoretical yield times 100%. I was giving you a percent error. So it's the actual yield over the theoretical yield times 100%. So if your actual yield is 100 grams and your theoretical yield is 100 grams, that's 1, right?
Yeah.
Times 100%, that's 100% yield. That makes sense, right? If you only get 50 grams, but you could have got 100, 50 over 100 is a half. Half times 100 is 50%.
Mm-hmm.
So this is how this works. So in this problem, they give us all the numbers. They say the theoretical yield is 68 grams. The actual yield is 16.3 grams. So to get our percent yield, we take 16.3 grams, divide it by 68.0 grams, and multiply times 100%. And we can see that this is roughly going to be 1/4, right? Or 25%.
Yeah.
There's a design flaw in my calculator. So I get 24.0% when I round. Is that what you got?
All right. Yeah, 24.
Okay, so that's how you get theoretical yield. That's all there is to it. Doesn't look that bad, but again, we didn't have to calculate the theoretical yield, did we?
Yeah.
So the next problem says refer to the book. We're not going to do that. So here, this is a practice using percent yield. So what mass of hydrogen is required to produce 1 liter of methanol? which has a density of 0.7191 grams per milliliter, if this reaction has a 74% yield under certain conditions. Okay, so what does 74% yield mean? The 74% yield means that we will get 74 grams of methanol actual for every 100 grams of methanol theoretical.
Okay.
How do I know it's 74 over 100? Because the definition of percentage means out of 100.
Mhm.
So you can see that this allows me to convert between the theoretical and the actual, right?
Yeah.
So they want to know what mass of hydrogen is required to produce 1.0 liters of methanol. Now, is this 1.0 liters of methanol going to be our actual amount we want or a theoretical?
It's theoretical.
I think it's actual.
Oh, wait. So,
What mass is
oh,
required
I
to
see.
produce 1 liter, right?
Yeah.
So I want 1 liter actual.
Okay.
So we want 1.0 liters of methanol actual. So I'm going to convert from methanol actual to methanol theoretical. Are you with me there?
Yeah.
The reason
So,
I'm going to convert that to theoretical is because if I start off with enough hydrogen to make this much theoretically, I will actually get that amount.
okay. Okay.
Now, we have a little bit of a dilemma here because this is how much we want actual, 1 liter. And we can convert this to this theoretically, because what I mean by that is this percentage could also be 74 liters of methanol actual to 100 liters of methanol theoretical. So we could use this. This 74% could be in grams or could be liters or liters. But let's pretend we don't know this. And that means we're going to have to convert this to CH3OH. Since it's in liters, we're going to convert that to milliliters. Then we're going to convert that to CH3OH grams. And this is all actual. Now I'm getting a little spread out here. So what I'm going to do is I'm going to take all of this and I'm going to write it out as follows. I'm going to start off with we want to get 1 liter. Is that right?
Yeah.
Okay, so I'm going to start off with 1.0 liters of methanol actual. I'm going to convert that into milliliters of CH3OH actual. I'm going to convert that into grams of CH3OH actual. And then I can use this to convert it into grams of CH3OH theoretical that I want. And then once I have this, I can get moles of CH3OH. And then I'm going to bring this on down, get moles of H2, and then I can get grams of H2, because I think originally that's what they wanted. What mass of hydrogen is required? So this is a long roadmap, isn't it?
Yeah.
So I'm going to squish it all together here with 1.0 liters of C. You know what I'm going to use for this? I'm going to use the letter M, E for methanol. Actually, screw it. I'm just going to write CH3OH. Okay, so now there's 1 liter of methanol actual per 1,000 milliliters of methanol actual. So here I'm getting rid of the liters and I'm putting it into milliliters. And the reason for that is because the density is given in grams per milliliter. So I'm going to multiply by 0.791, 0.791 grams of methanol actual per 1 milliliter of methanol actual. Then I'm going to multiply by 74 grams of methanol theoretical, and I'm just going to put a T there for theoretical, over 100 grams of methanol actual. And then I'm going to multiply by the molar mass of methanol, which is a 12.01 plus 4.04 plus 16.00 for a total of 32.05. So 32.05 grams of methanol on the bottom to 1 mole of methanol on the top. And this is theoretical. And then from the balanced reaction, we have a ratio of 1 methanol to 2 hydrogen. So 2 mole of H2 theoretical to 1 mole of methanol theoretical. And then hydrogen is 2.02 grams per 1 mole. So it's really tiny here, but I got it all written. And we can kind of estimate the answer. I like to make my life a little easier. So do you see this 100 and this 1,000?
Mm-hmm.
That's
10.
10. So I have 10 on top now. And you see this, I think what I'm going to do with my 10 is 10 times 2 is 20. 20 times 2 is 40. Now, I don't like 40 in all of the rest of these numbers, so I got to figure that out. So I guess what I'm going to do with my 40 is I'm going to do 0.791 times 40 is about 32. And guess what 32 divided by 32 is?
1.
1. So now I've only got my 74 left, right? So I'm thinking the answer is going to be around 74 if I did my estimating right. Okay, so let's see, 1,000 times 0.791 times 74 times 2 times 2.02 divided by 100 divided by 32.05, and I get hot diggity damn 73.8. And since this is 1, I get 74. 74 grams of hydrogen theoretical. How's that for an estimate? Okay, so this is the kind of work you would expect to see. Now, for a problem like this, let me show you another way to do this that would also be acceptable. So we're going to break this into 2 parts. The first part is going to be, number 1, figure out how many grams of CH3OH theoretical you need to get 1.0 liters actual. And then 2, once we figure out that, figure out grams of H2 theoretical to get the grams of CH3OH theoretical. So that's how we're going to split it up into 2. And for a problem like this, when you have a conversion going like this, it's probably best to split it up into 2.
Okay.
See how these 2 ways of doing it are make sense? So here, if we want 1.0 liters, and I'm going to do this. This is an abbreviation for methanol, MEOH.
Okay.
If I want 1 liter of methanol actual, I'm going to convert that into milliliters of methanol actual. I'm going to convert that into grams of methanol actual. And then I'm going to convert that into grams of methanol theoretical. And the reason I'm doing all of that is because I know it's 74 grams theoretical over 100 grams actual, or excuse me, the other way around. 74 grams actual per 100 grams theoretical. So that's why I'm doing all of this work. I'm going to put an A for actual. Okay, so I'm looking back at this problem and I'm thinking I may have messed this one up. Yeah, I messed this one up. Take a look at this. 74 grams actual over 100 grams theoretical.
Oh,
So the actual on the bottom,
yeah.
but that should be 74 and that should be 100, which means it's not 74. So let's go back and correct that.
Okay.
And you can see that if I got to take my original answer, divide it by 74 and multiply it by 100, I think the answer is going to be 100.
Yeah.
So let's find out. I don't think it's quite that easy, but it'll be closer to 100 than it is to 74.
Okay.
$135. So 135 grams theoretical.
Okay.
Okay. This one I think we're doing correctly. 74 grams actual for 100 grams theoretical. Remember, the actual amount you get is always less than the theoretical. Okay, so let's do this one. We have 1,000 times 0.791 times 100 divided by 74, and we get 1069 grams of methanol theoretical. Now, this would normally be rounded to 1,100, but we're not going to do that yet.
Okay.
So this is number 1. And then number 2 is going to be, we're going to take our 1,069 grams of methanol theoretical, convert that into moles of methanol theoretical, convert that into moles of hydrogen theoretical, and convert that into grams of hydrogen theoretical. Now the molar mass of methanol was 32.05. Two moles of hydrogen to 1 mole of methanol. And then 2.02 grams of hydrogen per 1 mole of hydrogen. Now, in this case, I don't necessarily think that the T is needed because all of this is theoretical, right?
Okay.
But I put it in there anyway, so I'm just going to leave it. So times 2 times 2.02 and divided by 32.05, and I get 135 grams of hydrogen theoretical. And actually, I need to round that to 130 grams of hydrogen theoretical. And the reason is because this is only supposed to have 2 zig figs. And when we go back to this problem, you see how this only has 2 zig figs? So this should also have been 130 grams of H2 theoretical, because the answer here was 134 point something. So if you did it this way and broke it up into 2 parts, or you did it this way and did it all at once, I don't care.
Okay.
This one stands to reason that it might be easier to break it into 2 parts.
Yeah, I think so too.
Okay, so that's number 24.
Yeah, I can tell I'm gonna have to practice that kind of thing a lot.
Yeah.
It's not like the math isn't hard, of course, it's just knowing what to do.
Let's do this last one, okay? Or do you have time for one more, or do you want to quit?
Oh, no, I don't have to go to work till 4, so I'm good.
Okay, we'll do one more here. So we have a 2.634 gram sample containing impure copper 2 chloride dihydrate is heated. The sample mass after heating to drive off water was 2.125 grams. What was the mass percent copper 2 chloride dihydrate in the original sample? This one is really hard.
Okay.
So we're going to draw a little picture to show what's going on. So here's our original sample, and this is the copper 2 chloride dihydrate part, and this is the other part. And I know it's impure because it says so, right?
Yeah.
Now we heat this, and we're going to have to make an assumption. And you know how they say, don't make assumptions because it makes an ass out of you and me?
Mm-hmm.
That's not the case in science. In science, we want to make good assumptions. And we're going to assume that this other part, which weighs X grams, nothing happens to it. No water comes off of it. What happens to the copper 2 chloride? It becomes copper 2 chloride with no H2O. And so we put plus 2 H2O out here because of the 2 H2Os here. So, are we good so far on this?
Yeah.
Now, notice it says heating to drive off the water was 2.125 grams. So this is 2.125 grams. And this is 2.634 grams. Is there any way for us to figure out the amount of water? the mass of water in there?
Oh, yeah. So if all the water is gone, then you just subtract the 2.125 out of the 2.634.
Right. So the mass of water is going to be 2.634 grams minus 2.125 grams. So that looks to be about 0.409 grams.
Mm-hmm.
Okay. Can we take the 0.409 grams of H2O and turn that into moles of H2O?
Yeah.
Can we take the moles of H2O and turn that into moles of copper 2 chloride dot 2H2O? Well, let's find out. If I write copper 2 chloride 2H2O, 1 mole, does that mean that that's equal to 1 mole of copper 2 chloride and 2 mole of H2O?
Yeah.
So that means that if I know how many moles of H2O, I can figure out how many moles of copper 2 chloride. Are you with me there?
Yeah.
And then if we have the moles of copper 2 chloride, can we get the grams of copper 2 chloride? Dot 2H2O. What do we need to go from moles to grams?
Molar mass.
Molar mass. Now, why do I need this? And the answer really is in the question. What's the mass percent of copper 2 chloride dihydrate in the original sample? So that's the question. What is the mass percent? So the mass percent of copper 2 chloride dihydrate in the original sample is going to equal, so I'm writing this all out with words, the mass percent copper 2 chloride dihydrate in the original sample is equal to the mass of copper 2 chloride dihydrate in the original sample. Sounds like I'm saying the same thing again, but I'm not.
Mm-hmm.
I'm saying the mass percent is equal to the mass divided by the mass of the sample times 100%. So if your sample is all copper 2 chloride dihydrate, and let's say that's 100 grams, and your sample is 100 grams, 100 over 100 times 100, 100%.
Okay.
Mass in here is 50 grams, and your original mass was 100 grams. Your mass percent is 50%. So with this equation right here, what do we know for certain? We know that the mass of the sample is 2.634 grams. So we already know that number on the bottom. We just have to figure out the mass in the original sample. And this is the way we're going to go about doing it.
Okay.
So let's do that 0.409 grams of H2O times 1 mole of H2O per 18.02 grams of H2O times 1 mole of copper 2 chloride 2H2O per 2 mole of H2O. And then the molar mass of copper 2 chloride is going to be 63.55, I think. Is it 55 or 85? 55 plus 70.90 for the 2 chlorines plus 18.02 and plus 18.02. So times 170.49 grams of copper 2 chloride dihydrate per 1 mole of the same. So if we estimate this number, doesn't 18 go into 170 about 10 times? 10 times 0.4 is 4. 4 divided by 2. So our answer should be close to 2. Probably a little less. $1.93. So what do we do with that number here? We take that 1.93 grams, divide it by 2.634 grams, and then multiply by 100%. And I get 73%. And that's it.
Okay.
So I told you this one was difficult, and the difficulty is trying to figure out how to work with all the numbers and what they're actually asking for.
Yeah.
So here, where you really should start is right here. What is the mass percent in the original sample? So here's where you want to start, is down here, where the mass percent is the mass of copper 2 chloride in the original sample divided by the mass of the original sample. And then when you look at that, you say, oh, I know that number. That's 2.634. So now you just have to figure out the mass of copper 2 chloride in the original sample. And that's the tough one.
Mm-hmm.
And here, what we did is we just figured out how much water we had. And I told you we could take the grams of water, get moles of water, and then figure out how many moles we have over here. What's the one big assumption that we made here? The big assumption is this, that all of this water came from here. None of it came from here.
Yeah.
If some of it came from here, we can't do the problem.
Okay.
So I suppose if you were a smart aleck, you could say, well, I don't want to make any assumptions, so I can't do the problem. But that's not what you're supposed to do. You're supposed to assume that the other part does not react.
Okay.
Okay, that was a really challenging one.
Yeah.
Now, of course, if you want to find out if you can do this one, is don't look at your notes and see if you can do it.
Yeah.
But also, when you're doing it, don't do it from rote memorization. Do it thinking, okay, here's why I'm doing this. Okay?
Yeah.
All right, so here's another one that's similar to the one we just did. And maybe you can give that one a try too.
Okay.
All right, we'll see you next week. You have a good weekend.
All right. Thank you.
Bye-bye.
Bye.